Okay, for test one, we got chapter 11 to go through, and there are just tons of formulas. So yes, I do allow 1 page of notes, the 8.5 by 11 standard form, not feet by feet, but inches by inches, and front and back. Should be plenty of room for you. Learn how to write small in some cases. Bring your magnifying glass. But we'll go through section by section here. First of all, there will be 13 problems. So each problem, I'll count 5 points, and then it'll be out of 65 points instead of out of 100. Like, well, of course, Calc 2, I don't think we ever had a test for 20. Maybe one of them was, but most of them were shorter than that. Section 1, well, section 1 and section 2 kind of go together. 11.1 was vectors in a plane. And section 2 was basically the vectors in space after we introduced the space, what they call space coordinates. So the X, Y, Z coordinate system. So we'll kind of pull all this together because we're doing the same thing with vectors in a plane or in space. And then there was a little bit of stuff that we only saw in one section or the other, but most of it we saw in both sections. So first of all, the graphs and writing of vectors. Graph or write vectors given initial and terminal points. Again, either 2-dimension or 3-dimension. Basically, you start with your terminal point and subtract the coordinate from your initial point. And the x differences in the x values give you your I component. The delta y is your j component. Delta z is your k component. Of course, by now, this is probably easy stuff for you, or at least should be, maybe. Magnitude. Find the magnitude of a vector. Again, your square root of the difference squared, and add up all those squares of the differences. Finding a unit vector in the direction of a certain vector. Well, the unit vector, basically your vector given divided by the magnitude of that vector. Okay. Again, whether 2 dimensions or 3 dimensions. Now, finding the direction, this is where kind of splits off from one dimension. Section 1, 2-dimensional vectors or the 3-dimensional vectors. So the direction of the 2D, basically find theta usually from the x-axis, describe it from the x-axis, from the positive x-axis. In 3D, we have direction angles. I guess that's later on in section 3 we actually run into that, but 2 dimensions, the direction can be represented by theta. In 3D, we also started looking a little bit more about parallel vectors. Are vectors parallel? We could have seen that in section 1 as well, but I don't think there was any problems like that. But definitely in section 2 we began that idea, and then of course later on we see that a lot more in section 5 when we're using vectors to describe lines or planes in space. So that's just the basics for now, starting with the vectors. In 11.1, kind of hit that now. We didn't look at this so much in section 2 and 3 space, but we focused on it more, the resultant vector, the resultant force of a vector system, the applications there. So possible application from, here's 2 vectors working on a something. What's the resultant force in maybe, let's see, 2 ropes or chains holding on to something? What's the resultant force that keeps the weight from falling? So something like that. Okay. So vectors, introduce vectors in a plane and in 3 space. And then section 2 we did a little bit more with just your graphing in 3 dimensions, graphing points. You'd have to be able to graph points to be able to graph a vector in 3D. But then distance between 2 points in 3D. Which is really how we calculated the magnitude of a vector in 3D. Also, kind of an important thing for 3 dimensions, find your midpoints, midpoint between 2 points. That's really just the average of the mean value of your x coordinates, your y coordinates, and your z coordinates. So now both of these kind of lead us up into our first equation representing a 3-dimensional object, and that is the sphere. Equation of a sphere. Which looks an awful lot like a circle. We just have the z part in there. Okay, but several problems that we found the equation of a sphere given certain conditions. Here's the center, here's the radius. Well, probably won't be quite that easy, but something to do with the characteristics of the sphere, find the equation, or in reverse, given the equation, find the center and radius. Now, in those types of problems, you're probably going to have to do some completing the square. So make sure you know how to do that. Okay. And these, again, first 2 sections, a lot of just the basic idea of vectors and notations and so forth. By now, it's probably old hat, but don't forget to write down the formulas just in case. Okay, section 3, of course, we'll need to be able to calculate a dot product, whether in 2 dimensions or 3 dimensions. This anymore goes, won't say 2 or 3 dimensions. It's either or both, probably both. But dot product, using the dot product, we can find the angle between 2 vectors. So a nice little formula for that. I always have to look that one up myself, so you better have that on your paper, even if you think you know it. Now, we have the angle between 2 vectors, and then in 3 space, we were given what's called the direction angles of a vector. So know how to find those, your direction angles, or sometimes called direction cosines, because it's all dealing with the cosine of the components. So make sure you're able to find those. Couple other things. One important part about comparing angles, or not angles, vectors, determine if 2 vectors are orthogonal. If they're orthogonal, what happens?
They're perpendicular.
Okay, perpendicular. How do we show whether they're orthogonal or not?
It's 0, right?
Dot product is 0 for orthogonal vectors. Questions along those same lines, whether the vectors are parallel. How do we show vectors are parallel? No clue. That's when one is a scalar product of another. If you can factor out a value from all 3 parts. And perhaps they're neither orthogonal nor parallel. So, and then about the only other thing we talked about with the dot product, but again, a very important concept, the projection of a vector onto another. Now, definitely make sure you have the formula there. I always have to look that one up myself. And then we saw this in some of the applications, that truck on the incline, 10-degree incline or whatever, something like that. Basically, what's the force keeping that truck from sliding down? Well, that's your projection onto the incline. So make sure you know how to do those. Okay, questions on section 3. And section 4, good old cross product. Definitely find the cross product of 2 vectors. And the cross product turns out to be a vector, but how does that vector compare to the original 2? The cross product is orthogonal, perpendicular, orthogonal to the two vectors that you've taken the cross product of. Okay. Which will help later in section 5 when we're trying to find the equation of a plane. You probably use that quite a bit, if you remember. Let's see. Cross product also is used to find the area of the parallelogram. Parallelogram spanned by two vectors. Basically, that means put your two vectors here and create a parallelogram. Okay. The area of that would be the magnitude of the cross product. So again, another formula for you to write down. Like I said, there's a ton of formulas. Everything's kind of interrelated, but to make sure you get the details down, it'd be a good idea to put that. Then that's more just two dimensions. Well, you could find the area of a parallelogram spanned by vectors in 3 dimensions. But let's see where we ended up with a 3-dimensional object. The parallelepiped, if I can spell it, parallelepiped, take 2 vectors and then create a third vector and you get a 3-dimensional, a box, not necessarily a rectangular box, but parallelepiped, you can find the volume. Okay, and you may be asked to find the volume of a parallelepiped spanned by 3 vectors, or here's a bunch of points representing the vertices of these of this parallelepiped. Find the volume. Well, in that case, you'd have to find 3 vectors all emanating from one point, and then maybe we have another vector over here giving it the 3rd dimension. I'm not going to try to draw that. I've told you many times this is why I don't teach art. So. But anyway, now to find the volume of the parallelepiped, we use what's called the triple scalar product. Which is actually, of the 3 vectors given, let's just call them U, V, and W. U doesn't necessarily mean unit vector in this case, but 3 vectors. It's the dot product of one vector with the cross product of the other 2. And you could go ahead and do the cross product and then do the dot product between the result with U. Or you could just set up the 3 by 3 determinant without the I, J, and K up top. Just use your vector components for each row. And then the value of that, the absolute value, volume needs to be a positive number, but the absolute value of that triple scalar product is the volume of the parallelepiped. So that's one application, a couple applications, the area of the parallelogram or the volume of the parallelepiped. But we also had one little bit more real world application for the cross product, and that's the torque. So make sure you know how to find the torque of a force applied and find the torque about a certain point, or in physics terms, that would be the moment of a force about a point. So, and again, if you need to write down formula or write down an example or whatever you need to put on that note card or page of notes. So, okay, questions on section 4? Okay, now lines and planes in space. Section 5, we get into the algebra of 3 dimensions. Equations of lines in space. Well, you found out that wasn't all that easy to do, not like a line in a plane. We found either parametric or symmetric equations. Make sure you're able to write out each set there. The line needs to be described. Well, it's basically just a point on the line as well as a vector in the same direction as the line. Get the right combination of that, of course. Again, write it down. From here, we look at how can we tell if the lines are parallel or even identical. Some sets of equations of lines look different, but they actually represent the exact same points. So make sure to know how to do that. We also looked at where or if 2 lines intersect, and if they do, find the point. Now in the homework they also said find the angle between the lines. I'll limit this to just find the point of intersection. If you do that, that's plenty good. If you can do that. But now you guys will get that, no problem. That was pretty much what we did with lines. Equations of planes. Definitely know how to find those. And for that, we looked at a lot of different characteristics. Given 2 vectors on a plane, or given even 3 points on a plane, given some description of a plane parallel to the YZ coordinate system. I mean, all kinds of different descriptions from our homework problems. So any of those descriptions would be a possible problem for the test, finding the equation of a plane. The main thing, again, like the line, we need to know a point on the plane, and then a vector not parallel to the plane like we did with the line, but a vector perpendicular, or what we call normal to the plane. So both the line and the plane, we need to know a point and a vector, but make sure you know which one's which. So vector normal to the plane along with the point. Now with the planes, we also looked at showing whether the planes are parallel orthogonal. Actually, I think we would call that perpendicular if we're comparing planes, but turns out we look at the normal vectors and see if the normal vectors are orthogonal, and if they are, then the planes are perpendicular. Or perhaps neither, always that possibility. Now, in section 5, we had a ton of other types of problems in the homework. I will at least eliminate some of those for the test. No distance problems, like distance from a point to a plane. Don't worry about that. No intersecting planes. Those types of problems were what's the equation or the parametric equations of a line of two intersecting planes. We won't go there for the test, so don't worry about that part. You have plenty of other things to worry about in section 5. Okay. Questions on section 5? And probably everybody's favorite thing to do, not mine neither. Surfaces in space, given an equation, sketch the graph of it in 3 dimensions as best as possible. Again, I'm not an art teacher, so I'm not going to expect you to be perfect on this, but at least somewhat get the right axes correct, or the right, if it's a parabola, make sure it looks like a parabola and not a circle, something like that. But we looked at a couple different things. The cylinder, which anything with only 2 variables would be considered a cylinder. If it's a circle in two variables, then it's going to be a right circular cylinder in 3D, because the variable that doesn't show up in the equation, well, it could be anything from negative infinity to positive infinity, and then the rest of it's going to look like the circle at each level, what we call the level curve. And but make sure and be able to draw that, whether it's a circle or it might be a parabola. It might be, if it's a line, then the cylinder would actually be a plane. So, interesting definition that we saw with the cylinder. And then, of course, the really exotic ones. Well, actually, we haven't seen the really exotic ones. The real exotic ones for us that we had to do were the quadric surfaces. And that was that list of, was it 6 in a couple pages there? They gave us the basic format of the quadric surfaces. Yeah, the ellipsoid, hyperboloid of 1 sheet, hyperboloid of 2 sheets, elliptic cone, elliptic paraboloid, and then the really fun hyperbolic paraboloid. Now, I will say I'm not going to try to make you do a hyperbolic paraboloid, but any of the others would be fair game. No hyperbolic paraboloid. The saddle, as sometimes we call it, paraboloid. Paraboloid, yeah, that's how you spell it. So, any questions there? About 4 or 5 of them, right? No. Oh, no? Okay. Maybe just one of those probably be sufficient. And then finally, 11.7, changing coordinate systems. cylindrical, and spherical in there. And of course, we will be using these later on in the semester, but make sure you can convert from one coordinate system to another, whether it be rectangular to cylindrical, maybe spherical back to cylindrical, or back to rectangular. I mean, any of those combinations. And possibly just a single point, or possibly turn an equation from one system to another. So lots of formulas once again. Your one page probably should be full. So now tomorrow I don't have anything before class, so I'll be over in my office until class time. So if you want to get started early, come see me over there. We can get you started, and then we'll come over here at 9:30. And if you want to stay later, I've got Calc 1 upstairs in 207, but you can keep working on that. I don't think no, their review is Friday, so tomorrow will work. Should be fairly quiet in there.